Generative AI is moving beyond simple conversation. We are now building agents to actively execute complex, multi-step tasks on our behalf. Think of an AI agent like hiring the smartest, fastest intern in the world. They can crunch endless spreadsheets, organize massive filing systems, and draft reports in the blink of an eye. Yet, for all that processing power, this same genius intern will occasionally make bizarre, catastrophic mistakes on tasks a human wouldn't think twice about, like telling a patient with respiratory failure to wait 48 hours before going to the emergency room. If we want to hand over crucial business operations or life and death medical decisions to these systems, we have to look under the hood and understand exactly why these specific, uncharacteristic failures happen. Deploying an AI agent safely means realizing you can't just write better code and walk away. You have to treat the technology exactly like that brilliant rookie, capable of incredible work, but requiring structured, intentional supervision. This chart shows the performance shape of large language models, or LLMs, in production. LLMs are AI systems trained on vast amounts of text to understand and generate human language. Notice the peak in the middle. That densely packed area is where the AI handles textbook routine cases perfectly. But out here on the flat tail ends, performance drops off. This is the inverted U blind spot. An agent processes standard invoices flawlessly, but encountering a slightly modified duplicate, it confidently processes it anyway, making a silent error where stakes are highest. That brings us to the second major blind spot, the gap between what an AI agent thinks and what it actually does. When an AI processes a prompt, it generates a reasoning trace, a step-by-step log of its logic. Often, an agent correctly identifies a critical warning in that reasoning trace, but then turns around and outputs a final recommendation to do absolutely nothing. Because AI models process logic differently than humans, we can never assume their stated internal reasoning guarantees a correct final action. The third blind spot occurs when an agent is forced to mix hard data with human language. We call this anchoring bias. Imagine an agent objectively analyzing vendor risk based on strict financial metrics. If a senior vice president adds a casual note to the file saying, "I'm confident this is the right choice," that positive social framing can heavily skew the agent's final assessment, causing it to ignore the actual data. This vulnerability to language leads directly to the fourth blind spot. Developers build guardrails to keep agents safe, but often those guardrails trigger based on the mere appearance of safety rather than an actual risk taxonomy. An AI monitoring company emails might flag a perfectly safe public press release simply because it contains the phrase confidential financial data. Meanwhile, if an employee exports 50,000 customer records but labels the folder Project Backup, the agent lets it slide because the text looks benign. Because these agents are so easily swayed by human social cues and surface-level keyword patterns, standard accuracy dashboards that just check the final answers will miss these invisible biases completely. If standard accuracy tests can't catch these errors, we need a specific layered management architecture to keep our AI interns on track. Layer 1 is progressive autonomy. The AI processes routine tasks automatically, while complex edge cases route to a human. By running the AI in shadow mode on those extreme cases, it learns the actual components required, safely expanding its capabilities over time. The second layer is deterministic validation. Instead of asking the AI to double-check its own work, you implement traditional, rigid, rules-based software checks completely outside of the AI model. Think of this external rule engine like a structural spell checker. If the AI's internal reasoning trace identifies a high-risk jurisdiction, but the final output classifies the file as low risk, the rules-based engine instantly catches the disconnect and halts the process. Combining targeted human oversight on the rare edge cases with rigid old-school rules monitoring the logic creates a containment zone that keeps the AI's actions strictly grounded in reality. Once you have that containment zone, you can build the third layer, a continuous learning flywheel designed to permanently eliminate AI errors as they happen in production. This involves manually reviewing the AI's mistakes, especially false alarms where it flagged something safe as dangerous. By analyzing those specific failures, you update the system's core rulebook, ensuring the agent learns the nuance and never repeats that exact error. Finally, the fourth layer is factorial stress testing. Rather than waiting for the agent to fail in production, this is a method for proactively finding the system's breaking points. Developers intentionally feed the AI practice scenarios injected with confusing social cues, false safety vibes, and contradictory data to see if its logic holds up. Setting up progressive autonomy, rigid deterministic rules, a learning flywheel, and stress tests requires a significant amount of upfront effort. But if you are deploying AI in a high-stakes enterprise environment, it is the only responsible path forward. These safety nets turn an unpredictable rookie into a reliable professional. This infrastructure allows us to deploy these